Hi there. So in this video, we want to talk about a different kind of quote unquote multiplication of vectors. We call it a product, and it's called the cross product. One important thing about this early on is that this is a vector product, meaning that whenever I take the cross product of two vectors, I get a vector. And so for that reason, some people call this the vector product to help remind them that you do get a vector as the result. So it's a very different thing than the dot product, and it helps us solve different types of problems. So let's look at what we're talking about. Okay, one thing early on to get into our brains is that the cross product is three-dimensional, is a three-dimensional operation. Now you can solve some two-dimensional problems with the cross product, but in terms of especially visualizing it and how it works, we need to be willing to go into three dimensions. Now what the idea here is, you can think about having a two-dimensional operation. So you could have two-dimensional vectors like this in the xy plane. But if you, so say this vector, I'm just going to talk about u right now. So say u's components are u1 and u2. Okay, the thing is in some, at least in some sense, I got to convert this into three dimensions. And so the thing is, u and v would be down in the xy plane. Okay, and so u might be pointing like this, and so we would need to rethink about its coordinates. It would still have u1 and u2 because those are the x and y coordinates. But since that thing is in the xy plane, then the z coordinate would be 0. So we would just incorporate a third coordinate of 0 if we're in two dimensions. Okay, so let's talk about what the cross product finds. Okay, so the basic use of the cross product is, say I'm given two vectors u and v that aren't parallel. We'll worry about that later, but just right now we don't want them to be in a line with each other. And the basic use is to try to find a third vector that's orthogonal to both of them. And just remember, orthogonal is the same as perpendicular. Okay, so the idea here is I might have to put in a sub video that has better pictures, but let's see how we do with this. Okay, so we're out in space and we have these two vectors u and v. So let's say they're not even at the origin. They're out here. So say v is here. Now again, you got to remember we're in three dimensions, so it could be coming in and out of the page. All right, and let's call this vector u for now. And then here's another vector. Say it's going really into the page, so it's going into the screen really well. Okay, so the question is there a vector that's orthogonal to both of those? Okay, and if you think about it, the vector kind of coming out this direction right here, that would be a vector that's orthogonal to both of those vectors right there. Okay, but that should start leading you into something. I could stretch that vector. I could do a scalar multiple. That's not going to affect the angle between those vectors. So I could have just as easily, I could have a vector that's out here. So there's already more than one answer. Even from that picture, there's actually infinitely many vectors that are orthogonal to both of those. Okay, but there's nothing that dictates which direction it should also go. So you can see, if you can visualize that line right there, any vector that's along that line is going to be orthogonal to both v and u. So this problem, as stated, there's not a clear answer. There's actually infinitely many answers. Okay, and that's a nice thing to know. It's called the orthogonal space. But given two vectors, any vector that's on the line perpendicular to those two vectors will be a third vector that's orthogonal to them both. Okay, and so the key thing is with the cross product, in defining what the cross product is, we do want to just get only one vector. Okay, and what we need to do is we need to first specify which direction it's going to go. Is it going to go this way, or is it going to go that way? Okay, and then we also need to specify how big that cross product vector is going to be, i.e., we need its direction, just like with all vectors, and its magnitude. So when we first see the definition of the cross product, that's what it's going to involve. We're going to see a coordinate-free definition that that gives the direction and the magnitude. Okay, so here we go. If we're given vectors u and v, we're going to define the cross product of u and v, and we denote it with the old x multiplication symbol, and that's part of the reason it's called the cross product. Now for the definition, what this vector is, u cross v is, it's orthogonal to both u and v, but as we saw, there's infinitely many vectors that are orthogonal to both u and v, so we need to be more specific. And so we get the direction of the cross product with the right hand rule of rotating u into v, and I'll show you what I mean by that in a moment. Okay, and then its magnitude is given by this quantity right here. And this is actually a physical quantity that helps us with some geometry problems I'll explain in a moment. But just remember that whenever we say theta, we're talking about the angle between u and v. All right, and so the idea here is that if I have, again, imagine being out in space, so we have some axes somewhere. But say I have vector u right here, like that, and if I draw them so that they have the same tail, so then there would be vector v. Okay, so all vectors that are orthogonal to both u and v are on this line right here. Okay, like that. And now to get the direction of u cross v, I think about taking my hand, and pointing my fingers along u, like that. But I want the open part of my hand here, okay, my palm to be facing toward v. And then remember what I do, I curl those fingers in whichever direction my thumb is pointing. If I stick it straight out, that would be the direction. Now I haven't drawn perfectly here, but that's telling me that u cross v is going to be going in that direction. All right, and now in order to understand this magnitude right here, I'm just going to tell you what it is. I can explain to you where it comes from, but what that quantity actually is if I draw the parallelogram connecting u and v, or determined by u and v that we've seen before with adding vectors, and find its area. Okay, if I were to compute its area right here, the area of that parallelogram is actually this quantity right here that I was pointing out a moment ago. So the area of that parallelogram right there is actually equal to the length of u times the length of v times the sine of theta. Okay, I can briefly explain where that formula comes from. To get that formula for the parallelogram, since you know vectors u and v, you know what, at least in practical situations, you would know how long they are, what their length is. Okay, but to do the area of a parallelogram, the formula is base times height. So you can see right here, could be the base, and so there's base right there. But we don't know what the height is because this is a slant line. So to determine that, what you do is you draw altitude coming down here like that, and there's the height of that parallelogram. Well, the height of that parallelogram is actually, you could go through the trig to show, is actually the length of v sine theta, which comes about right there. All right, so that's the idea of the cross product without coordinates. So let me try to show you this with a slightly better picture. So here I have a three-dimensional coordinate system right here, and I have these two vectors drawn. This is the vector u right here. This is the vector v right here. And so I'm going to form their cross product. You might want to wait a minute and stop a minute and think, convince yourself what direction the cross product goes in. So whenever I take the cross product, I'm going to get that vector right here. Okay, and so notice that it's following that right hand rule of rotating u into v. Okay, and then numerically how long that is, I draw the parallelogram determined by u and v. And although the units are different, the area of this parallelogram right here is the same as the length of my cross product, u cross v. So that's the idea about how you can get the length. And what this will allow us to do, too, is once we can do cross products in coordinates, then we can compute a cross product to determine areas of parallelograms and even triangles and more complicated objects. Okay, so now the question is, we typically do have coordinates. So say I have the coordinates of vector u and the coordinates of vector v. How can I compute u cross v? And the formula is a little bit complicated looking. Where it comes from is, remember that u and v both are supposed, or u cross v is supposed to be orthogonal to both u and v. So you can set up a system of equations based on the dot product needing to be equal to 0. The problem is that system of equations that has infinitely many solutions. That comes about from that geometry I showed you, that the orthogonal vectors all have to lie on a line. So there's infinitely many possibilities. But once you add those extra conditions of the direction and the magnitude, you're able to solve the system. Okay, now this one is going to look complicated. I can show you ways to make it look simple, but it is a little bit complicated. And so there ends up being using 3x3 determinants to make computing it a little simpler. But what u cross v is, remember it's a vector with 3 components. So the first component is u2 times v3 minus u3 times v2. Okay, like that. And then the second component is going to be u3 v1 minus u1 v3. Okay, and then the third component is going to be u1 v2 minus u2 times v1. So it looks pretty complicated, but you can see some patterns here. That notice in the first component, none of the subscripts equal 1. They're all 2s or 3s, and then they reverse around on each pair right here. Okay, like that. And see, the same thing happens in each component. In the second component, there's no subscripts of 2, and in the third component, there's no subscripts of 3. Now, the only thing is, you got to remember that things, if you're seeing the pattern, things reverse around in the second component. And so notice you always, in the first and the third component, you start with the smaller subscript and then to the larger one. And then they reverse around on the subtraction side. And that happens in the first and the third coordinate, but in the second coordinate, they reverse around. So it's just one, so you can see it can be hard to keep up with. I've just done so many of them that I have that pattern down. Okay, now I'm not going to go into this in this video, so you might have to look up more about 3x3 determinants. Okay, but what I can do is to compute u cross v. This isn't a real determinant because we have vectors and numbers. Usually there's just numbers in the determinant, but what I can do is I can put the vectors I, j, and k on the top row, like that, and then I put the components of u in the second row. Now remember, it's the order that you do a cross product in is important, and so you got to make sure and put the things in the right order. The first vector goes in the second row, the second vector goes in the third row. Okay, and so the idea now is that you expand on that top row, and so you get I times the 2x2 determinant, where you cross out the row and column that I is in. So we get u2, u3, v2, and v3. And then whenever you expand along the top row, you subtract in the second part, and that's the reason that, or that's not the reason, that's a reflection of that pattern reversing in the second coordinate. And then you have j times the 2x2 determinant, where you cross out its row and column. So you get u1, u3, v1, v3, like that. And then plus k times the 2x2 determinant from crossing out its row and column. u1, u2, v1, v2. Okay, and I typically don't mind if people use the calculators to compute these too. On most calculators, at least the CAS ones, you can do cross products. Now you won't type that on your calculator, but the command for the cross product is cross P. You do a parenthesis. Calculators use square brackets, not angled brackets. So you type in your first vector, close that bracket, make sure to put a comma in between the two vectors, and then you put in the components of that vector. So it kind of depends on your tools. We'll be using cross products to do other things, so I won't mind if you just type them in on your calculator. But however you do it, let's just try one by hand so you can see. So say I have the vector 3, 1, negative 5, crossed with the vector 2, 4, 8. We'll get a big cross product with that though. Okay, and so what I do is I set up that determinant, I, j, and k, and then I put the components of u, or the first vector, in the second column, and I put the components of the second vector in the third column, like this. Okay, now I'm just going to expand on that top row, so I get I times the 2 by 2 determinant, 1, negative 5, 4, and 8. I cross out the row and column that have, let me just show you that in case you haven't seen it, but I cross out the row and column that I is in, and so notice I'm left with 1, negative 5, 4, and 8. Okay, and so then I just keep going on the j. Just remember you subtract the j term, or the middle term. Okay, cross out its row and column, and I'd have 3, negative 5, 2, and 8. Like that, and then plus k times, cross out its row and column, I'm going to have 3, 1, 2, and 4. And then the idea of a 2 by 2 determinant is you subtract the cross products. So you do this product minus this product right there. Okay, and so we would have 8 minus negative 20, and then minus j times 24 minus negative 10, like that, and then plus k times 12 minus 2. All right, and so what's that going to be? That's going to be 28i minus 34j, and then plus 10k, like that. Okay, and you might leave it in the IJK notation, or you could convert it back into the angle bracket notation. 28, negative 34, 10. Now, how can you check your answer is right? At least you can check the orthogonality, that your answer should be orthogonal to both of our given vectors. So this should be orthogonal to this vector, and this should be orthogonal to that vector. Remember, we talked about in the last video how you can determine orthogonality. You take the dot product, and the dot product should be 0. So yeah, now let's just look at some of the basic uses of the cross product. And so the first and most common one is to find an orthogonal vector. Okay, so often we'll have two vectors, like that, and so I'll just stick with my u and v. And there's going to be some reason that we want a vector that's orthogonal to them. And I'll show you one of the more important ones in a minute. I didn't draw that line very well though. So all the orthogonal vectors are on that line, and so the easiest one to find is u cross v, sorry, like that. If you think about the right hand rule, that vector would point in that direction right there. This is a let me show you. First of all, you'll see later we'll be talking about planes in space, and when we want to get equation. And the way to one of the most common ways to specify a plane is to get 3 points that are inside of that plane. And so the thing is a vector that's orthogonal to that plane basically determines the direction of that plane. We'll talk about that later. But the way you can get that orthogonal vector is just to take one of the points to be the common tail, and then form 2 vectors from that using the other 2 points. And then whenever you find that cross product, you'll get this vector. This one's kind of hard to draw for me, but you'll get this vector that points up, and that is orthogonal to that plane. Okay. Another common use of the common product is what is used for what's called moving frames, or local coordinates. And so say u and v started out orthogonal. So again, remember that I'm drawing this in trying to draw this in space. But you have 2 vectors out here. They start out as orthogonal, and they both have length 1. Okay, like that. And so that would be your u and your v. Okay, as long as I start out with length 1 and those 2 vectors are orthogonal, then whenever I take that cross product, not only do I get another orthogonal vector like that, but its length would also be 1. Again, I'll explain this later. If you want to see that, remember that the length of u cross v is the length of u times the length of v times the sine of theta. Okay, well, if these started out as length 1, you're going to have 1 times 1, like that. And if they're also orthogonal, you're going to have the sine of 90 degrees, which is also equal to 1. So that length would be 1, like that. And what that allows you to do is, since these have length 1, these are kind of like acting like an ijk locally. And again, there's a lot to this story. I don't want to like that. It kind of acts like a local ijk, and so what you have are some a set of 3 vectors that kind of act like an x, y, and z. And the idea is that if you have something moving in space like that, there's just context where you want, that's called a local frame or a moving frame, and so you want some coordinates that move along with that object as it moves in space. Okay, and so another common use is in geometry. It can find areas of parallelograms and triangles from just coordinates without having to go through the trigonometry. And if you remember, with that coordinate-free definition, the length of u cross v is the area of the parallelogram determined by u and v. Okay, so let's look at a case right here of a parallelogram. Let's just do it in 2 dimensions, and so it's pretty easy to do. Okay, so I could have a parallelogram whose whose vertices are at 1, 1 and at 4, 1. Okay, and then another set of vertices at 1, 3 and 5, 3, like this. Okay, and for some reason I might want to be finding the area of that parallelogram. Okay, and so what you can do is form the 2 vectors that have a common tail right here. Okay, and I could call those u and v, like I usually do, like that. And so u would be the vector from the second point, or from the first point to the second point. So I do tip minus tail, and so I have 4 minus 1, comma 1 minus 1. Okay, which is 4, 0. All right, and then if I have v, this is going to illustrate something else since I'm in 2 dimensions right now. And so then if I have v, it's the vector that starts at 1, 1 and goes to 2, 3. All right, so I'm going to have 2 minus 1, and the y coordinates would be 3 minus 1, sorry, like that. So I get the vector 1, 2. Now remember, to do a cross product we need a 3-dimensional vector, and so I can convert this to 3 dimensions just by adding the z coordinate equal to 0. All right, so now to get the area of that parallelogram, I need the length of u cross v. Okay, but the first thing I would do, now that I have coordinates, I can compute u cross v right there. All right, and so you might want to pause and see if you can get this cross product here. But for my x coordinate, I'm going to have 0 minus 0, and then for my y coordinate, I'm going to have 0 minus 0 as well. And then for my z coordinate, I'm going to have 8 minus 0. So I get 0, 0, 8. All right, now notice that's a vector. Now, there's a couple things to point out. If you start with 2-dimensional vectors and convert them to 3 dimensions, whenever you take the cross product, the x and y coordinate will always be 0. All right, but now we realize that's a vector, so that's not the area. The area is the length of that vector. And notice that since I only have a z coordinate, that length is easy. And just remember, if we're doing area, that's square units. Okay, like that. Now, just because I'm running out of space, I'm not going to go through the whole thing. But this also does triangles. Also for triangles, if you remember, a triangle is half a parallelogram. Okay, so same thing here. So the area of a triangle determined by u and v, we got to be a little bit careful, is going to be 1/2 the cross product of u cross v, like that. All right, and so let's make sure we know what we're talking about here. So if I have a triangle determined by 3 points right there, then I would want to go through that same process I did a minute ago. Draw two vectors that have the common tail, like that. I forgot to draw my triangle in there. Let me go back. So say here's the triangle I'm trying to do the area of. Okay, like that. Then like I started to say, and I stopped myself, I draw the two vectors that have the common tail right there. So those are your two vectors that I'm referring to up in that formula. So I'd call that u and v. And then the area of that triangle would be the magnitude of their cross product. All right, and there's also an application in physics. There's a few applications, but the basic one is to deal with what's called torque, and you've probably heard of torque related to car engines. But people use the Greek letter, and it's called tau to denote torque. Okay, but the idea here is the easiest diagram. You may have seen this in a book too. So just imagine having some bolt, and then you want to either unscrew it, loosen it, or tighten it. So you have a wrench here that you're going to apply. So what's the idea here? Depending on which way you turn it, you're going to apply a force either this direction at the end of the wrench, though that's the key thing. You might do it this way too, just depending on if you're trying to loosen it or tighten it. Okay, so the key thing is you have this point on that wrench that you're applying that force at. Okay, so that determines a displacement vector. You have this displacement vector right here for how far away on that the directed distance, that's what a displacement is, for how far away you are applying that force. Okay, like that. And then there's just this basic formula that the torque is equal to the displacement vector crossed with the force vector. Okay, so I'm going to leave it there for now. As far as we go in our math class, we'll mostly use those cross products for those orthogonality properties that we're looking for. But there is lots of application to the cross product as well. So anyway, I hope that helps, and I wish you the best, and let me know if you have any questions.